Okay, welcome everyone. I guess you can hear me and you can see my screen, hopefully.
Yes.
Excellent, thank you, Gaetano. So, welcome to this first webinar of CG Twin. It's a real pleasure to welcome you here on Google Meet. Thank you to all the partners for the organization of this workshop. So this is, well, as I mentioned, the very first edition of a webinar in the context of the project. We are now reaching well, more or less the middle of the project. So we have some interesting items to showcase publicly. And the agenda we have today is quite exciting. So on my side, I will not talk too much. I will just introduce the project, the main objectives, and what are we supposed to deliver, let's say, in the 3-year time frame of CG Twin. But then most importantly, we will have three quite good speakers actually talking about first the network digital twin architecture we are employing the project. So this work will be presented by Paola from imec. Then we will talk about basic models for digital twins. So we see we introduce today quite a lot of different notions related to this digital twin universe. This one will be introduced by Ayat from LIST. And then we will talk about the evaluation framework we have developed in the project. And this one will be introduced by Gaetano from Politecnico di Bari. Then we will conclude with some remarks. So, well, I guess you're already all familiar with Google Meets, but yeah, if you have any questions, if you have anything to ask during the presentations, just use the chat functionality of Google Meets, and then we will do our best to answer at the end of the session. But of course, if there is any burning question, we can answer right after each individual presentation. But let's start now with the welcoming. So on my side, my name is Sébastien. I come from LIST, so the Luxembourg Institute of Science and Technology, and I'm coordinating this project. And I just would like to spend a few minutes now to give you some background on digital twinning. What do we call digital twin? I mean, it's a buzzword today, and I think it's good to start with a baseline. Start with the same concept, right? So first of all, and I guess that's quite popular if you are active in this field, not necessarily only the SNLGO community, but in the ICT field. The digital twin, in general, this is a digital replica of the physical activity. So the idea is really to create a sandbox of this process, it can be an application, it can be a network, and use this sandbox as a way to test different scenarios, optimizing them before applying the best parameters, let's say, to the That's the first definition. So a digital replica. The idea is also to have this digital replica, let's say, existing all along the life cycle of the entity to be replicated. So not only, for instance, in the case of a network, not only when the network is operated, but also during the design phase, during the production phase, operation phase, and then disposal phase. So we could use, for instance, this kind of replica to try to, let's say, anticipate, predict what could happen if some new entities are introduced. So, of course, this is extremely close to the traditional simulation paradigm. So we can use simulation systems quite wide. And so the idea now with digital twins is to create real-time interfaces with the reality, so that we can benefit from real-time data and then also control the reality thanks to that. There are many domains that have been promoting these digital twins. The first one historically has been the manufacturing domain. This started a few years ago, but then, as you certainly know, we have also this kind of digital twins in the agriculture domain, in the healthcare sector, mobility, more recently in the network domain. But these are the typical things you can do with a network digital twin. So a digital twin applied to networks, so creating again a digital copy of an existing network. So you can do some simulation and planning. So how to best plan the future deployment of the network. In sense, think about the best locations. Nodes, parameters, smart. We can use it for real-time network operation and management. So how to save energy, for instance, on a given network in real time. So it is a bit close to today. Then we can also generate some data. We can use this digital tools as well to train AI models, and then for what analytics. This project, CG3, has been developed as part of the SNSGU community, which is quite an important community for us. If you are not familiar with this community, I really recommend you to visit. They are really driving the innovation related to 5G networks in Europe. So we are part of this. And if we have a look at all the projects that have been funded, actually there are 30% of them that report addressing or developing digital twin technologies. What we have done, when starting this project, is to review what is completely different. And what we can see is that most of the approaches are a bit a common, or let's say standardized definition of what is really a digital twin. And that's the problem we are addressing now with this project. So if we look at the standards, because we need to start from that, as you may see, it's quite recent. The first standards they are talking about digital twin is from 2018, so that was in the manufacturing domain. And if you have a look at the most recent iteration related to network digital twins, so how to standardize the architectures related to digital twins, but for the networking community or sector, this has been proposed by ITUT. So there is a recommendation there that has been released 2 or 3 years ago, which explains, what could be the different blocks related to digital twins, and this is the baseline we are using in this project. So we're not going to the details there because we have a full presentation on architectural work. But if you are interested by the topic, I guess that's a good reference to consult and to put your work on that. So the main conclusions, and that's what we try to address in this project, is that there is still a long way to fully rewrite the concept of digital twin. At the moment, we really consider on our side that, of course, it's not only a simulation, it's not something that is disconnected from the reality. This implies a complexity that is hard, to implement in reality. And most of the time there is a kind of duality between the risk of dreams, and the reality.
Sébastien, can you maybe try without your, because we can't hear you well. It's a little bit echoing, so sorry to interrupt you.
Is it better now?
Yeah, better.
Okay. So I will restart the presentation. No, that's fine. I will just continue then. So yes, I was just mentioning the needs, for further developing this concept of network digital twins. So yeah, the idea is also to demonstrate the application of NDTs into tangible use cases. So that's again what we are doing in the project. And we need to properly integrate this concept as well into the future AI-based architectures. And there you see different documents, different tables that are currently being developed by the community, again by ITUT. So the idea and the main objective of the project is really to go for that, right? To try to design, implement, and validate a reference architecture for future 6G systems that could incorporate this concept as a core mechanism. So the duration of the project is from the 1st of January last year to 31st of December next year. So again, we are really in the middle of the project. And this is part of the SNSGU project portfolio, phase 2. So meaning that we have quite a lot of results to present and still a lot to deliver. These are the partners that are participating in the project. So we have really a good balance between research entities, companies, SMEs that are participating. And that's it about the project. So very quickly, because I think I'm already exceeding a bit the time, These are the expected results. So I will not list all of them, but just to showcase that we plan to deliver some open source results, like a federated simulation engine, for instance, that could help the community, in further implementing this concept on their own. We also plan to deliver some blueprints of architectures, some models as well, and yeah, I guess this will be presented in more details by my colleagues. As I was mentioning, we have two demonstrators, two use cases, let's say, that are planned in the project. The first one is related to teleoperated driving, which is quite a challenge, when you have to anticipate the potential, let's say, failures on, all along the way of a teleoperated vehicle. And then we have a second use case related to energy efficiency, but again, my colleagues will slightly go back on this. So the first use case in more details, this really refers to like a predictive version of a digital twin. So let's imagine you have to teleoperate a vehicle. The idea is really to try to anticipate what could happen a few seconds or a few minutes or even a bit, before what could happen in terms of issues, network issues all along the way of a vehicle, let's say. So there, the idea is really to use prediction techniques to see and to anticipate, the quality of service available for the vehicle, and then to take a decision on how to best optimize that, considering many different parameters. And the second use case is more related to what is more real-time use case, let's say, so what we call a reactive digital twin. And there the idea is to adapt the overall end-to-end energy efficiency of the network, and in particular of the radio access network, I guess, since we all know that this consumes 80%, I guess, of the energy consumed by a network. So that's it. That was a long introduction. I hope it was clear, that the mic was not so much disturbing for the audience, but I guess now it's time for Paola from imec to talk about the architecture. Paola, the virtual floor is yours.
So good morning, everyone. I'm Paola Soto, postdoctoral researcher with imec and the University of Antwerp. And as Sébastien mentioned, I will talk about the architecture that we are proposing for network digital twins, right? Let's start a little bit with the motivation. So basically, 5G introduced many innovations, but still relies on manual configuration and lacks the intelligence needed for future demands, right? The 6G era, projected for 2030 roadmap, aims to be an AI native architecture, which is fully autonomous, right? And we are, as Sébastien already mentioned, we are heavily based on the ITU recommendations. And according to the ITU, for example, this level of autonomy can be achieved through an experimentation sandbox where multiple experiments can be carried out, and the network itself can learn what is best for its current state, right? And NDTs, or network digital twins, are central to achieving this goal by providing real-time intelligent representation of the network. Okay, so basically, in this project, the 6G team project, envisions an AI native architecture that integrates NDTs, network digital twins. By integrating them, we can create live intelligent replicas of the network that allow for real-time monitoring, predictive optimization, and autonomous control. And this synergy between AI and NDTs will greatly improve network performance, reliability, and security. So one of the most important aspects in this project is the creation of a kind of cyber physical continuum, where the physical network and the digital representation will interact seamlessly, unlocking new levels of efficiency and innovation. So Technically, the project is focused on federated graph-based NDTs, which means that multiple interconnected digital twins are working together, supported by a strong modeling and simulation framework. The 60 twin architecture basically is organized into 3 primary layers, creating a comprehensive framework for future 6E networks, right? Emphasizing the idea of closed loop control. We envision first in the top layer, let's say the human world, as a semi-open loop in which network operators or human operators basically can input the requirements and different network KPIs for different applications. In the bottom, the physical layer in charge of sensing, basically collecting data to create a given state and acting, right? So the optimizations are being fed to this physical network and then acting on the different devices, right? And the digital twin network in this case is responsible for the thing and planning, and everything is connected, of course, and supported by these control loops, let's say. We will briefly detail each of the layers. So, for example, in the top layer, the network applications or the human world basically represents the interaction between the network applications, such as Sébastien mentioned, teleoperator driving and energy savings, and the underlying network systems, right? It connects the users, the user-facing services, and the applications with the network infrastructure, facilitating enhanced decision-making and automated actions. Right? On the bottom, as I mentioned, the physical layer is a base layer representing the real-world infrastructure and its operations, including user equipments, surrounding environments, radio access networks, core networks, etc. Right? This layer can incorporate AI-based functions to enhance the performance and efficiency and possess basically sensing capabilities for data collection and acting capabilities for executing the decisions. And basically in the middle, the central component of 60 Twin project, acting as a sophisticated virtual replica of the physical network, we have the NDT. Basically, this layer focuses on data and model management to enable real-time analysis and optimization of the physical world. The NDT layer provides a safe sandbox for training and validating AI-based network functions and services before they are deployed on the real network, and integrates also with a technology agnostic simulation framework to generate synthetic data sets for advanced modeling and analysis. So basically, as you may imagine, there are a lot of challenges in creating these exact replicas of the network. In particular, during the execution of the project, we have focused on 2. So one is on data collection and harmonization, and 2 on the management and orchestration of all those instances. Regarding the data collection and harmonization, we basically acknowledge that the network is fast. We are dealing with highly diverse data sources, each with different formats and frequencies. Basically, the network infrastructure is also heterogeneous, mixing legacy networks and modern devices across the radio access network, for example, the core, the transport, the edge, the cloud. So handling massive real-time data streams at scale is really difficult. And we must ensure low overheads, avoiding redundancy and maintaining performance. So the kind of data is also heterogeneous in its structure and semantics. The harmonization basically means fusing this data into a consistent format while preserving the meaning of the data. We must deal basically with semantic drifts, different time scales, and refine it into what we are calling smart data models that are suitable for modeling and simulations. Finally, there are overarching challenges. So, for example, as security and privacy risk, they basically increase when sensitive data is shared or stored. So compliance, access control, and data integrity are also critical. And the distributed nature of networks basically complicates the orchestration and coordination. And if we integrate that into the AI models, basically that brings an additional complexity, like continuous model update and preventing unreliable outputs. Right? So based on that, at 6G Twin, we take again a layered approach to overcome these key data-related challenges. The first thing that we propose is to implement a telemetry framework, right, that supports various protocols. So I'm not going to give much details, but basically the main idea is to create kind of a dictionary between different protocols, basically, to create translations, and that all the different protocols can be understood, right? That is the idea behind this telemetry framework. This telemetry data layer basically will enable seamless data flow across the clouds to edge continuum, while ensuring compatibility and efficient resource use. And second, more in the digital network side, so to make our data architecture scalable, we recommend using distributed stream processing tools like Kafka and Zeno to manage real-time high throughput data across geographically dispersed networks. So data collection is made more efficient through target-driven and on-demand mechanisms, data reduction at the source, and advanced telemetry techniques, right? So the harmonization layer, the data harmonization layer, basically processes and structures the heterogeneous telemetry data into the smart data models. Basically, it creates a standardized data format and cleans and enriches the data sets and handles basically this semantic drift that I was talking about, ensuring consistency, fidelity, and interoperability. Four, to ensure basically standardization and interoperability, the architecture is designed with open interfaces and cross-domain integration via east and west and north and south interfaces. This facilitates basically the unified management across vendors and domains, right? To support basically the security and the privacy issues, we integrate the encryption, access control, and anonymization. Blockchains and federated learning can be also used here to enhance trust and data governance. As a second point, basically, I mentioned that we were tackling challenges in managing and orchestrating these instances. and basically this is due to three main reasons, right? So first, the network is complex and dynamic, right? So 60 twin demands managing highly dynamic multi-domain environments with the strict performance requirement, breaking traditional silos between computer and communication layer. Second, so basically the orchestration, so the AI ML orchestration. So deep AI integration adds lifecycle management challenges, such as ensuring transparency, adaptability, fairness, to handling continuous updates and synchronization of distributed AI agents. Third, basically the NDT lifecycle and fidelity. Basically, it is impractical to build a single all-encompassing twin, right? We must manage multiple instances of digital twins, so synchronize the states, maintain accurate data, right? Gain enough trust for autonomous decision making, etc. Right? And data management, for example, is another key aspect that we focus on. Handling massive distributed data volumes without overloading the networks, while ensuring integrity, privacy, and consistency. Basically, also including the federated and multiple domain orchestration. So the heterogeneous policy-driven domains, let's say, they lack unified standards that they can communicate with each other, complicating the coordination. So the resource optimization is also made more complex across different autonomous domains. So yeah, this is also a challenge into managing and orchestrating this kind of entities, right? What we are doing for that, right? Because talking about the challenges is super easy, but then what are we doing for that? So basically, we realized that there is no single entity that can address all the challenges that I mentioned before. So we propose a hierarchical management structure. Basically, we call it the 60 twin monolayer. Basically, this is an unifying layer integrating physical and digital components, right? So that contains managers for the different physical and digital components. So it combines federated management, different AI workflows, simulation frameworks, and the management of the NDT replicas, basically. So the NDT management, what it does is that handles the different life cycle of and orchestrating basically the multiple NDT instances. The data management ensures continuous real-time telemetry for dynamic model updates, and we added also an AI workflow management, which is in charge basically of the training using NDTs basically, or using simulator as a sandbox for the training and the validation of the AI-based functions, right? Before live deployment. So as I mentioned, yeah. So second, basically we distinguish between a running instance of an NDT and all the components that comprise it, right? So basically, an NDT instance is a combination of basic and functional models that relies on several key components, basically. We propose an NDT orchestrator that coordinates the creation and execution of the instance, a model manager, which coordinates the interactions between models, ensuring performance and triggering corrections, for example. A resource manager, which oversees the computing resources. A monitor layer, basically tracking the status of the NDT, detecting anomalies, issuing alerts of performance, for instance. And then we have a translation layer, which converts basically the human inputs for the NDT and the outputs into human readable information, right? So together, these components are ensuring smooth, efficient, and understandable NDT operation. Like I mentioned, for example, an AI training block, which provides alternative pipelines for most of the functional models, but also for the controllers that are going to be deployed, or the functions that are going to be deployed on the network itself. So this part of the system allows the models to learn from data, whether coming from the network or generated as a synthetic data set. Predicting changes, making adjustments, and continuously improving their performance, right? So these pipelines include specific variations suitable to each kind of functional models that we are working on, including probabilistic models, supervised, and reinforcement learning. So finally, we have more or less updated. So we started from a really basic functional architecture to this one that is a little bit more rich and more detailed, including more details. So basically, to handle all the fine-grained details that are centered around the digital twins, right? The 60-twin NDT basically is going to enable a powerful closed-loop optimization framework. We have 2 reference use cases, as Sébastien was mentioning. The project basically is going to test its solution and test some components of the architecture in the teleoperated driving use case, right? Basically, it's going to support a predictive NDT. It requires the vehicle sensors to transmit real data, environment information to a remote operator over the mobile network, necessitating low latency, high reliability, and robust data transmissions. The NDT helps predicting the radio coverage, enabling efficient resource allocation in the RAN, and optimizing slicing at the core network level for this scenario, right? The energy efficiency demonstrator, basically this use case explore strategies and technologies to reduce energy consumption in 6G networks. So basically the NDT is going to be fed with data collected from the network in different domains, in the RAN, of course, but also in the edge or in the core, including quality of service parameters, the system performance data, localization and sensing data, etc. So the NDT will generate basically RAN scenarios to train different AI agents that trigger the network optimizations for short term, such as at the cell or at the beam level, and long term, basically, to scheduling basically different energy options. So to power down some cells, for example, in case of low demand. Okay, so in general, so basically the 6G Twin project is a step forward toward AI native 6G networks, where network digital twins enable real-time optimization and management of complex systems. And by focusing on open architectures and standardized interfaces, we ensure that these solutions are scalable and widely applicable. We will deploy basically for future work, we will deploy the architecture in different test beds, validating the use case like I mentioned, the teleoperated driver and the energy savings. These deployments will test the closed loop intelligence, AI model performance, and the model update workflows. And finally, the insights from these implementations will basically refine the architecture and contribute to the 6G standardization efforts, hopefully, aligning basically with future industry needs. So that's it from my side. I give the floor then to my colleague Ayat, I think, right?
Yes, indeed. Thank you very much, Paola. Maybe in the meantime, because I see we are quite a lot connected, I mean, if there is any burning question, again, please use the chat. Otherwise, I guess we can switch to you, Ayat. Thank you again, Paola. So Ayat will talk about basic models.
So, hello, everyone. I hope you see my screen.
Yes, perfect.
Yes.
Yeah, so my name is Ayat Zakindi, and I'm a researcher at LEAST, and I will be talking about basic models in the digital twin. As Paola presented the architecture, you can see that there's a specific component for real-time representation of the sorry, I stopped presenting. Okay, can you see again? Yeah. So there's the blue box that we call it in the architecture that is responsible of representing the physical network in the digital domain, and it has several components like the unified data repository, basic and functional models. However, we have challenges in representing the networks, as Paola mentioned, also that we have a complexity in telecommunication networks because of the dynamics, because it has multiple domains. It has a lot of smaller network elements that compose the network. And also because of the lack of standardized approach for NDT data modeling. What we mean by that is that each vendor can have their own implementation of the network configurations or the network element, and if the data is shared between multiple vendors or multiple operators, then there will be some problems. So what we aim in this session is to just clarify our approach for creating a unified data repository for network digital twin representation. So before going into the basic models, we should talk about the data before, because data is what feeds the basic models of the network. So I will talk about a concept that is called data space. If you're familiar with it, it's like a marketplace to share data between a data provider and a data consumer. It has a set of policies that ensure governance and privacy of data between the sharing bodies. It's mostly a European term that is used to govern this data sharing. And as we can see that we have common European data spaces that has already been defined for health, manufacturing, and agriculture, but we can't see that there's a data space for telecommunication networks. So in order to create this data space, we first focus on the vocabulary part that is mostly like the data harmonization layer for the network digital twin. So here we use the smart data model a concept where it's a new description language for data models that harmonizes the description of data that is shared in one domain. And as we can see also here that there's a missing part where telecommunication networks are not present in the smart data models that we have today. So in this project, we are proposing to create this standard description of data harmonization using smart data models for 6G networks. So how do we start by doing this? We started by looking into the data that is generated from the network itself. Signaling data, for instance, they have many meaningful data for representing the states and the configurations of the network and the performance. So we can, as we can look into the network, each network is composed of smaller components that are called network elements. And if we go into the standards, and more specifically 3GPP standards, we can see that each network element is defined by a class that has a set of attributes, which are mostly the configurations of the network element, and measurements, which are more like the dynamic part of the network element that responds to the set of attributes that are set. So as a first step, we try to define a data taxonomy for network elements. And here I show an example of several RAN network elements where they have the class name, the description, and the attributes that are related to each class that are extracted from 3GPP standards, and the dynamic part, which are the measurements that are extracted from other standards. But then at the end, we merge them in order to get one class that has all of this information. So the key outcome from this proposal is to build a comprehensive model library for developing this unified data repository, and in order to integrate other contextual data from other data spaces, we propose to incorporate our data into these Faye smart data models and to create more interoperable approach for data sharing in network digital twins. Now, after we define this data taxonomy and structure, we can go into more details of basic models. So I haven't defined what basic models yet. So as you can see, it's written that it's a representation of network components and behavior, but this is this can be interpreted in different ways. So we have set two definitions for basic models in this project. The first one is that we have a basic model of a network element, which is the collection of data that describes its properties, configurations, and operational status, which what I've presented so far, to have this table with all the network elements listed with their attributes and measurements. But then we also have a basic model of the network itself, because the network is composed of multiple network elements from different domains. So we need to aggregate the basic models and see what are the relationships between them, and create the physical and logical relationships between them. So I will put it as an example because it's easier to understand. So we have a basic model where of the network itself. So we have multiple elements like the user equipment. We have the RAN, we have the core network, and we have the data network and transport network. So each one of them is a network element, but of course, each one of them is composed of smaller entities. So this one, we call it as granularity level 1. So if we dive deeper into each element of these components, we can see that, for instance, the RAN is composed also of multiple elements like the radio unit, distributed unit, and centralized unit, which are also associated to some protocol stack, and they have more elements to them. So this is the granularity level 2. And if we look deeper into the granularity level of network elements, we can see that we can also break down the network into really smaller entities, which are what are defined in the standards as classes. So if we represent each network element and its relationship with other elements, we can reach this vision, and we can see that the basic models are actually a graph-based representation of the network element. So what we learned here is that we need to have a structure that represents basic models in a modular way with a graph-based representation where it has the relationships between the different network elements, and we can have we should actually capture the temporal evolution of each network element, since the network is evolving, and we need to capture this dynamicity of the network. So how did we achieve this representation in practice? We used a tool that is called the GrayCat, which focuses on digital twins for real-time operations. It's mostly like a graph database that can evolve in time, and we can actually set it in a modular way where we can either instantiate the whole data class, or we can just choose the part that we are interested in modeling of the network. So here I just show an example of this development where we collected data from our 5G private network, and we instantiated this database with the collected data. Here we show that we have models for each network element, as I showed earlier, and it's connected with the relationships between the network elements. We can see also that we have this time evolving aspect to it. So I think this shows the tool, and I will move from here. I will talk a bit about the relationship between basic models and the whole NDT framework that Paola presented. So as Paola mentioned, that we can't have a digital twin that has all the elements and that represent everything in the network. So we need to instantiate instances that are relevant to the application that we consider. So if we consider that we have an application like a teleoperated driving, where we need to have some functional models like to predict the coverage or to optimize resource allocation, we need to choose only the relevant basic models and the data from these repositories in order to create this NDT instance. So as you see, the flow here is representing the NDT model management from the management framework. That first, the functional model is chosen from the application layer, but then the basic model and the basic model population are chosen based on the functional model that we have. And with that, we can create multiple network digital twin instances that can be then trained and calibrated based on the scenario that we have. So that was all from my side. I hope that I summarized the modeling aspects of the network digital twin, and I will leave the floor now for Gaetano to present.
Yes, Gaetano, I guess this is the last presentation of today. So again, if you have questions, that's the unique opportunity to address well, whatever you have in mind through the chat. So please do so. So Gaetano, the floor is yours. Thanks.
Thank you. Thank you, Sébastien. Thank you, Ayat. Let me share my screen. Okay. Can you see my screen?
Yes.
Yes.
Okay, good. Good morning, everyone. My name is Gaetano Volpe. I'm with the University of Bari. I'm a postdoc researcher. My talk will be about the evaluation framework of 6G. This is the outline of this presentation. So I will briefly introduce the work package 5 and the deliverable 5.1 in which we developed our evaluation framework. Then I will talk about the NDT evaluation objectives and the link with the ITUT Y3092-3091 recommendation that have already been mentioned by the previous speaker. Then I will introduce the FESTA-based approach for the evaluation of 6G twin, and finally I will briefly introduce the use case, although they have already mentioned, but I will do that in terms of the expected KPI. So the work package 5 is the work package 5 is the work package of the evaluation in the 6G twin project. So the main objectives are to develop the framework for evaluating the network digital twin and the new AI-based communication paradigm. The other objective is to specify the test scenarios and the test cases for the use case. And we have also a focus on the development of solutions for reengineering the network architecture and for standardization. The first outcome of the work package 5 is the deliverable D5.1, which has been already published, and it defines the evaluation framework, the NDT requirements, and the KPIs of the project. So the main evaluation objectives for the 6G twin mentioned in the deliverable are to judge whether one specific NDT can meet the application and use case requirements, and to assess the NDT capability level as recommended by the ITUT 3091 that has been already mentioned. If we look at the state-of-the-art in network evaluation, we find metrics like throughput, latency, packet loss, and jitter, and we see a broad use of simulation tools for optimization tasks. When we have an NDT, we have a very good advantage because we can provide a virtual replica of the physical network. We can simulate what if scenarios, and we can predict the performance, and we can apply optimization without impacting on the real network. Still, the ITUT 3090-3091 provides a very solid theoretical basis for the development and the evaluation of the network digital flow. This is the reference architecture that we find in 3090. As already mentioned by Paola, we have three different levels. So we have the network application level on the top, the physical network on the bottom, and in the middle we have the network digital twin. Of course, in the physical network layer, we have all physical and virtual network elements. In the application layer, we can create the NDT instance, and we can apply updates to the physical network to the NDT. And in the middle, we have our digital twin layer, in which we have the components that have been already mentioned. So we have the data, so the data repository. We have the data models, so the functional models and the basic model, and we have the entity management. Of course, this is the reference architecture mentioned in the 3090, and our architecture in 615 is a little bit more complex, and that's been already explained by Paola. In the reference architecture, we have four key enabling elements. So we have the data, so that provides a unified repository for training or to create the models, to create and manage the models. We have the mapping that allows us to have a real-time exchange between physical and virtual systems. We have the model that reflect the key features of the twin and physical entities, and we have the interfaces for communicating between levels. So we have southbound interface to connect physical and virtual networks, and northbound interface to facilitate exchange between the virtual networks and network application. What are the requirements and metrics for an NDT? In the ITUT recommendation, the first three requirements are fidelity, so the accuracy of performance metric compared to the physical network, the efficiency, so the model should be faster than real time and consume reasonable resources. This is the reason is that they have to, of course, to simulate different scenarios in real time. So they have to be very, very fast. And the other requirement is the flexibility. So they need to adapt to change. They need to be able to provide on-demand service, to collect and to store data in a flexible way. They have to allow to combine data models. They also should allow to communicate and interact with the other digital twin. And we have also in the NDT two kinds of performance metrics. So model metrics, for example, number of twins, size of information, system cost, accuracy, etc., and traditional network metrics that we have already mentioned: latency, packet loss ratio, link utilization, and so on. In 3091, we have a framework to assess synthetically the capability level at different levels of the network digital twin. We start with the top capability level taxonomy that is made of 5 NDT capability levels: L1, L2, L3, L4, and L5. L1 is the basic one, is the representation level, and L5 is the top one, which is the autonomy level. This is related to the overall network digital twin. So this is the final capability level. And in 6G twin, we aim to reach at least the L4, which is the optimization level. Of course, in order to assess the overall level, we have to evaluate lower levels, so more detailed levels. And so we go to the lower level, which is the dimension. In ITUT 3091, we have 5 sets of dimensions: data service, digital twin modeling, interactive mapping, intelligent user experience, and trustworthiness. And each of these dimensions is linked to a specific set of evaluation indicator, which is the last level that we find in the recommendation. These are some of the tables that you can find in the ITUT recommendation. And as you can see, there is a set of evaluation indicators for each dimension. Of course, each of these evaluation indicators has capability level, his own capability level assessment, and based on the capability level assessment of each of these evaluation indicators, we can assess the overall capability of the network digital twin. So we can easily split our assessment into detailed categories and assess individually the capability level of each of these evaluation indicators. Of course, we can, as soon as we have the individual evaluation indicator level assessments, we can calculate and compute the overall dimension level and the NDT overall level, as mentioned in the previous slide. As you can see, in the case of dimension level and NDT overall level, we can also fix some weights for the different dimension in order to give more weight to the dimension that we are interested the most. Of course, the procedure is detailed in the ITUT recommendation. How do we come to the capability level assessment? Of course, we have to collect data and compute some KPI. So we decided in 6G to use the FESTA V-shape methodology to handle the data collection management and the KPI computation. And as you can see, the FESTA V-process methodology, which is well known in the literature, so you find here the reference, is made of 3 main steps: the prepare phase, the usage phase, and the evaluation and the impact phase. In the prepare phase, we define research check question, we define use case, we define KPI, and we test scenario. In the usage phase, we actively collect data for KPI, and in evaluation and impact phase, we analyze the KPI and we compute the capability level assessment. And of course, we will see now in a while, we evaluate the socioeconomic impact which are the second part of our evaluation framework. In CG Twin, we have two kinds of KPI, so two categories. We have project KPI that are mostly qualitative and are linked to the milestone of the project. And of course, we have more technical KPI related to the use case, which are quantitative, so they can be computed in a mathematical way. This is the path to NDT capability assessment. So we start with the data collection, we evaluate the KPI, we link each KPI to the dimension and the evaluation indicator, and finally we assess the NDT capability level at the dimension level and at the global level according to the ITUT 3091 recommendation. We also have, as I was mentioning, we also have a complementary social evaluation approach. So we are interested on seeing the impact of the CG Twin project, and we are interested in capturing the stakeholder feedback, and in order also to prevent and to avoid redundancy with similar project in the SNS. So we want to administer some questionnaires to the relevant stakeholders in order to collect feedback and perform our social evaluation task. And we also want to contribute to the annual surveys of the SNS project to share our experience with the other project and examine the key value indicator and social acceptance of 6G technology. Of course, I mentioned that we have a quantitative KPI. These KPI are mostly related to the use case. As already mentioned by all previous speakers, we have two use cases in 6G Twin. The use case one is focused on teleoperative driving and is made of two different scenarios. So one in the lab, which is the predictive power adaptation, and is about teleoperating a single robot dog over a private 5G network. And the second one, which is an extension on the first one in a simulation environment. The second use case is energy savings in test deployments. Here we have three scenarios that have already been described by Paola. So we have the optimization in 6G radio access technology, which is the scenario one, the network management and control with heterogeneous radio access technologies, which is the scenario two, and finally the federated cross-domain radio and computing resource optimization, which is the scenario three. Both use cases have KPI that fall in one or more of these categories, and related mostly to network metrics. So we have, for example, data rate and the capacity, we have the latency, as I already mentioned, we have the service reliability and availability, the packet loss, the edge node utilization, the energy efficiency, the channel spectral efficiency, and of course we also have some KPI related to security aspect. So we have a set of KPI for each use case, and some are in common, but all fall in one or more of these categories. Okay, this concludes my talk. Thanks for your attention. If you have any question, I will be very glad to answer. Thank you.
Thank you very much, Gaetano. So on my side, I will just quickly conclude the webinar with a few slides, and then I see that we have a lot of questions in the chat. But let's first just give some information, because I guess this will have already answered to some of these questions. I guess you see my screen. Good. So something useful maybe for the audience following us. This is the overall timeline of the project. So again, we still have 18 months to work on the project. The most, I mean, what we have to achieve now is to switch from the concept we have presented today to the setup of concrete proof of concept. So this is a work that we are initiating now. And so this also means that we have generated quite a lot of results already. We have a few 100 pages of deliverables that are almost ready to be published. And I think this is one of the questions, you know, that was addressed. So the deliverables will become public in a few months' time. We first need to go through the midterm review of the project, and then the deliverables will be publicly released on the website. In the meantime, I guess you can also go through the Zenodo community of the project. We started to publish, you know, some of the results in scientific journals or conferences, and all these papers are of course accessible in open format. So that's the community. I posted the link. I think it's available in the chat directly. But yeah, you can also Google it. It's so at the moment we have 14 publications that are there, and they are all fully accessible. So if you are interested by what we have done so far, you can basically regularly consult this page. I think this is the most reliable source, let's say, when it comes to publications. So we really try to make it updated regularly, and of course, way more publications are planned in the future. So that was the first webinar, just to indicate, you know, before we switch to the Q&A, that we also have a target of organizing 5 other webinars through, you know, during the entire duration of the project. So we started today with this one. I guess, well, a replay will be available in a few days or weeks' time. But then I really encourage all of you to keep in touch with the 6G Twin community, with our social media on LinkedIn, because some other announcement might follow. And thank you to our partners, UBWare and R2M Solutions, to have organized that. Yeah, and I guess there it's just a simple way to get access to our website, the X account, and the LinkedIn webpage. So maybe now we can switch to the questions. I see some of them. So the first question is related to the deliverables. So again, this will be released quite soon. Then I see a few questions from Xavier. The first one being the difference between a digital twin network and a network digital twin. Well, I see Paola smiling. Maybe you have an answer for this one. I don't want to speak too much. Or Gaetano or Ayat, I mean, please feel free to give your interpretation.
No, it's nice to see Xavier connected. Basically, Xavier, in the project, I don't think we make a difference between the digital twin network and a network digital twin. Maybe across the deliverables we use the terms interchangeably, but there is no difference that I can consider there. Unless the colleagues here present, they have a different opinion, but in my opinion, we use them and to mean basically the same. I don't know, because there is also a question from Xavier a little bit in the back, or you want to go one by one?
No, please go ahead. Let's go with Xavier first, and then we see the other questions. And I see you very motivated for answering to these questions. So
no, the thing is that basically some related question. I also identified something that I can answer. So basically, Xavier also asked, what are the functions and vision for the AI in the NDT? So this is going to be a personal opinion, because this, for example, is something that we still need to discuss in the consortium. But in my opinion, basically AI can be used in the NDT to predict the future states, to basically give advices to the network operators. So as I was mentioning, we consider more or less a human in the loop, right? Because the network digital twin is going to help this, in my opinion, will help to adopt AI more safely and to gain more trust in the AI, let's say, to be implemented directly on the network. So I see network digital twins as a intermediate stage where the user is the one that is interacting with the digital twin, right? So in this sense, the digital twin has to offer solutions to the user that maybe generates alerts of this anomaly is going to happen. So take actions like this and this and this, right? So in that sense, for example, the functions and visions for AI is to predict. So for example, anomaly detection is one. Predictions or classification, for example, of traffic, to improve a little bit of security in networks. That could also be functions that are envisioned for the NDT. And ultimately, so basically what we want to achieve, but I think in my opinion that is a really long shot, is how to make that the NDT actually takes control of the physical network, right? But like I said, so these kind of decisions and these kind of suggestions and advices are actually implemented without the need of the human in the loop, right? But like I said, I think that is a really long shot, and yeah, we are working towards that.
Thank you, Paola. So let me see the other questions. So yeah, coming back to digital twin network and network digital twin, I guess this can really be used in a, I mean, this means the same. I think some of the literature is using digital twin network as a means to say a network of several digital twins, you know, not necessarily a digital twin of the network, but then it's almost a philosophical debate. So, I mean, the papers are really using them in a similar way. The next question is, if you are only collecting data, how can this be considered a model of the RAN? From Puria. Ayat, do you have an answer there maybe?
Yes, I see that Puria has two questions. One before it, what kind of model is required for the ORAN radio unit, and does it capture the behavior? So yes, as I defined the basic model, maybe I didn't go into the details, but we also capture the behavior of network elements. So if it's needed by the application to optimize, for instance, the baseband operations, then the behavior is also considered in the basic models. And if we are only collecting data, how it's considered, then as I showed that we have this graph-based database, and whenever we collect data, we map these data to this representation, and we keep historical data also. So at the end, it will be used to feed a functional model, and we haven't talked about functional models in this particular session. But if we have in the future more sessions that talk about functional models, it will show how we use this data to create the whole NDT instance and model the system that we want.
Thanks. I see two other questions from Farouk Hassan. So related to the first use case, The objective is considering assist autonomous vehicles. So does it mean it will be edge assisted, sensor assisted, human assisted, or cloud assisted? I guess this will be edge assisted. This is the current definition of the use case. So we really consider that the vehicles, can progress in an environment where you have roadside units, edge computing units deployed all along the way. And so the idea is to optimize the behavior of these edge units, how to optimize the energy consumption, how to, let's say, optimize them in a way that, the vehicles are always connected all along their way. And the second question is also related to that. So is it is planned to be active or passive digital twin? I guess there you are referring to predictive or reactive digital twin. So basically something, acting in real time or with a delay, let's say, so that you can predict what could happen, what if analysis scenarios, etc. So I think for this use case, the basic assumption is to use a passive digital twin. So more a kind of super accurate prediction tool so that we can have a concrete plan, for these edge nodes to, for instance, switch on or off at the right moment. But we are considering different other sub-scenarios there. Gaetano, do you want to provide more details there?
No, so it's of course the what we envision is an edge assistant environment framework. So the digital twin will be passive. So just to complement what Paola was saying, just to link it with the digital twin, in use case one, we already have some concrete examples of the AI-based functional model. For example, we propose in some of the first publication an AI-based models for coverage prediction, for example, in order to keep the connection alive throughout all the path. And we also provide some solution to combine the AI-based models in CG Twin with existing AI-based model, for example, for traditional route planning. So we already have some concrete examples of some concrete first example of AI-based functional models.
Thanks. I see a last question from Israel Lever from Aalborg University. So one of the main challenges with digital twins is model selection, indeed, since we will end up with a larger library of different models, I guess. Are you doing some work on model selection and evaluation for specific network elements? The software you presented seems to support several models, but I guess that these have to be selected by the user. So there are different approaches there, and I think this is related to the NDT manual you presented, Paola.
Yep, I can also take that. Yes, actually, yes, we are working on something related to model selection. So basically, in one of the papers that I am working on, what we consider is this pre-deployment stage, right, where you have different models. So basically, I focus on one specific use case, and it is for basically auto scaling using reinforcement learning. So we have different reinforcement learning models that are they are different in sense of they are using different reward functions, and they are also using different algorithms, and they are all kind of fitting basically more or less what the requirements of the user is asking, right? So they balance a little bit between the amount of replicas and a QoS parameter, which is in this case is latency, right? So we consider actually that this pre-stage deployment of this controller can be evaluated actually using a digital twin, and that is what what we do. Basically, we create a digital twin from the network that we are going to where we are going to deploy the controller. We train the algorithm, and then we assess to compare them across all the different algorithms and reward functions, and finally then we can proceed with the deployment. So yes, we are kind of considering that into the research in the project. I guess that's what is more difficult, because, for example, here I consider homogeneous models, right? So, for instance, reinforcement learning. So all the reward functions and the algorithms are based on reinforcement learning. But then it would be more difficult because, for example, if we are using different models. So, for example, scaling can also be modeled as a predictive use case, let's say, where you predict the demand that you're going to be having in the future, and then you adjust the number of resources or replicas in this case to your predicted demand, right? So if we want to compare, let's say, between a supervised learning model and a reinforcement learning model, so that would be a little bit more tricky, and we will need a little bit more of research, but yeah, at least we are doing something about that. So thanks for asking.
Thanks. And I guess this will be the very last question or remark from Farouk Hassan. Edge-based passive DT is good, but it can also have better application with DRL, so deep reinforcement learning based DT that enable reactive approach. Yes, sure. But so again, the idea of the project is not necessarily to work on an infinite number of use cases. The main objective is really to elaborate, the foundations of this network digital twin concept, to come with a reference architecture and to validate, the different components of this architecture. So the basic idea of having two use cases was to have well, an active and a passive use case, so that we can really validate the different components and the different facets of what the architecture we are working on. So of course it can be, we can also come with a real-time approach, and I guess we may have time, to explore that during the project, but that's not the priority. We have a certain number of KPIs, things to measure, to evaluate, and yeah, at the moment we are just following this methodology with the two baseline use cases, we have elaborated. But the good thing and the main message is that we are fully open to collaborate. So if you are interested, be it well, you, Xavier, or all the audience, I still see 24 people connected, do not hesitate to reach out. We are extremely happy to have bilateral meetings to see how the results of the project can benefit to you. So, and that's the objective of this webinar. So thank you again for all of you for your participation. Thank you to all the amazing speakers, to the organizers. And again, this session has been recorded, so I guess it will be published quite soon. Thank you all. Have a nice day.